Welcome to lecture 12 of thin film deposition module. In this lecture we will continue our discussion on chemical vapor deposition of thin film deposition process. If you recall, in the previous lecture we had looked at that how the transport of gases into a chemical vapor deposition chamber might affect the deposition uniformity. So, for any chemical vapor deposition process, or it is based on a chemical reaction. So, we need to have two approaches or two very important aspects. One is the transport of the reactants and the reaction itself. Okay. Now, most of these deposition are done by gas phase reactions. We could also use liquid phase reaction, but liquid phase reactions will be very uncontrolled for thin film deposition, because in liquid phase the reaction rates are much faster and we cannot control the transport. Okay. In gas phase we can control the transport of the reactants to the substrate where they form a thin film, so that our growth rate or deposition rate is controlled and we can control the properties such as thickness and morphology of the thin film. Okay. So, two very important things, one is transport of reactants and second is the reaction thermodynamics of the reaction. Okay. So, in the previous lecture we had seen that how boundary layer plays a role. When the gas is flowing on its surface, it forms a boundary layer, and how that plays a role in the how the reactants are distributed in the chamber. Okay. In this lecture we will discuss how this formation of boundary layer affects the uniformity of the thin films. So, as you see that in this figure here we have a tubular reactor in which the reactant gases are coming from the left, and we have kept the wafers on which we want to deposit thin film along one of the chamber walls in axial direction. Okay. Now, the transport properties of the reactants will dictate how the thin films are growing. Okay. So, the equation that governs the flux, let us see, this is a two dimensional state. We are going to ignore the third dimension, which is in perpendicular to the plane of paper. So, how the reactants are distributed in these two dimensions, x and y. So, this is y axis and this is x axis. Okay. So, now the flux of the species, of the reacting species at any point in reactor will be governed by two things. One is the mass flow and second is diffusion. Okay. Mass flow in the bulk and diffusion across the boundary layer. Okay. Now, we can use these expressions to and the fixed second law to have the concentration with time, how the concentration is with time is changing at different locations inside this reactor. Okay. So, this is a fixed second law equation, and we can solve this equation with these boundary conditions to get the distribution at any given time with x and y, and this is a steady state. Okay. Now, the boundary conditions are such that any reactant which reaches the wafer reacts very immediately. Okay. So, the reaction conditions such as temperature and thermodynamics of the reaction are such that any reactant species which reaches the wafer reacts almost instantly. So, there is no buildup of the concentration of reactants at this boundary. Okay. And also at this C is x equal to 0, the concentration is constant because the gases are flowing coming in from the left. So, at this x equal to 0, the concentration is constant, and at this boundary there is no concentration gradient along this direction. Okay. So, these are my boundary conditions, and if we solve this partial differential equation in these with these boundary conditions and under the assumption that my velocity and this b is more than diameter and pi or the diffusion constant into pi. So, under these assumptions which are valid, we get this distribution of concentration in x and y. Okay. At any given point we know how much concentration of the reactant is present. Okay. Now, flux at y is equal to 0 will be converted into thin film, which can be converted into film growth rate. Okay. So, any concentration at y is equal to 0, the flux in this direction will be converted to thin film. Okay. So, if we know this Cxy, then we can so this is dy. If we have we know the distribution of flux of the concentration, we can calculate the flux coming onto the wafers at y is equal to 0. Okay. So, this is the flux, and this flux, which is number of atoms or molecules of the reactant per unit area per unit time, we can then convert using this this expression into film growth rate. Okay. This is the film growth rate, this is the flux. M is the molecular mass of the M is the mass of thin film species. Okay. And Ms is the mass of reactant species. So, for example, if we are using silane to deposit silicon, M would be the atomic mass of silicon and Ms would be molecular mass of silane. Okay. So, and this is the density of the thin film. So, using this these two expressions, we can have a growth rate or deposition rate of the thin film as a function of x. X is this direction. Okay. And then you can see that it has an exponential dependence with a minus sign with x, which means that my deposition rate is decaying exponentially with x. Sorry, this would be the, so this is my g of x, right. And since the deposition rate is decreasing exponentially with x, my deposition rate at various points or various wafers would be different, and I will not have uniformity. Okay. Now, how do we counter this problem if for some reasons we are bound to have a reactor like this? What we can do is that rather than keeping wafers at along the axis, we can keep the wafers at an incline. Okay. So, this is my gas entrant and these are my wafers, okay, at an incline such that the boundary layer thickness also decreases as you move along this axis, okay, along the wafers, and you can achieve some kind of uniformity. Okay. This is one way of controlling the uniformity if you have large number of wafers. For the single wafer and a small wafer, it will not matter, but in production we want to deposit on a large number or large area at one time to save the cost. So, we can use this. Okay. Now, let us look at another geometry of thin film deposition. Many a times we use a tubular reactor and vertically stack our wafers to have thin film deposition. So, such an arrangement is shown in this figure here, in which silicon wafers on which we want to deposit thin film are stacked vertically in a tubular reactor. Okay. And so, gas flow is from the left, the concentration at the surface of the first wafer is C0, and we want to know what is the radial distribution or radial uniformity of the thin film deposition on each wafer. Okay. And there are certain parameters like delta, which is the separation between two wafers, and the radius. Okay. Now, I will not go into the details, but if you look here, this gives you an expression that how the thickness or the deposition rates will vary along the radius. And again, if we say that my thickness is governed by mass transport, not the reaction, then it will be how the concentrations are distributed along the radius. Okay. So, C0 is at the outer surface of this wafer, because gases are flowing outside and then they will move in, right. So, the gases are mostly flowing here, and then they will go inside and spread and then go out and then go in, right, for reaction. So, C0 is the concentration here, and Cr at any radius. Okay. So, C0 is at R0 at the periphery, and this is the ratio between the two, where I0 are the Bessel function of 0th order. Okay. We do not need to worry about this. If you know this quantity in the brackets which is given, then you can find what is the Bessel function of that quantity in a standard mathematical table of Bessel functions. Okay. What is important is this factor here, okay, because it is here and here at both places. This depends on the radius, delta, and the diffusivity of the reactants in the gas phase. Okay. Now, if you look at here, if phi is very small, you can see that deposition is very uniform. Okay. If phi is very large, then you have very vast difference in the deposition rate. Okay. Relative thickness varies a lot along the radius. This is R over R0 of the wafer. Okay. Now, what does phi small mean? Phi small means that your radius is high and K reaction rate constant is high, so that it does not depend on the reaction rate, and your delta and these are small, R0 and K are small. Okay. And so that if the reaction rate is slow, then it gives enough time for the gases to diffuse. Okay. And also diffusivity is high, and also the separation between the wafers is high. Okay. So, you can calculate using these quantities to some extent what would be your radial deposition rate uniformity in this kind of reactor and arrangement. And these are very often used to deposit silicon oxide on a large number of wafers in one go. Okay. So, this is about the uniformity with the geometry of your reactor and number of wafers. Now, let us have a look how this also depends on the temperature, because we had said if in the previous slide that if the reaction rate is slow, then you will have more uniformity. Okay. Now, let us look at that aspect, how the temperature dependence helps in uniformity and thickness uniformity. So, in this picture, if you see that my substrate is vertical like this, and this is my film deposition. So, this is formation of film. Okay. My gases are flowing in the bulk perpendicular to paper or this plane of the screen. Okay. This is my boundary layer at the surface of the substrate where the film is growing, right. So, you will have a boundary layer because the gases are flowing, they will form a boundary layer at the interface of substrate. Now, so from the gas phase transport from bulk to the substrate, which is the substrate concentration at the substrate, will depend on the concentration difference, because this is through diffusion, and we have used a term Hg. Okay. Hg are gas phase mass transfer, okay, which is also related to diffusivity of gas in gas phase. Okay. So, this is gas phase mass transfer across the boundary layer, okay, and we have assumed that this is constant flow. So, we can maintain the Cg in the bulk flow always. Okay. Now, at the surface, whatever is the flux, we do not want the buildup of concentration here, so that this concentration difference drops below a certain level, then it will stop the diffusion. Okay. So, there will be a so if there is more concentration here, then the reaction rate will be higher, and it will try to keep the same flux from the gas phase. Now, the flux which is being consumed to convert this gases into film will be depend on the film deposition rate. Okay. So, the film deposition rate will depend on the concentration at the surface and the reaction rate. Okay. So, how fast the thin film is growing or the reactant is converting into thin film will depend on the concentration at the surface and also the reaction rate. Okay. Now, in steady state, to avoid any buildup of concentration, both of these fluxes should be equal. Okay. So, whatever coming in from the gas phase is reacting at the surface to give you thin film, so that this Cg minus Cs will remain constant, okay, and that is your steady state. In steady state, if you solve this using this equation, you will get an expression like this. Okay. So, where Cg is constant. Okay. Now, the concentration at the surface will depend on the ratio of Ks over Hg, means reaction rate over mass transfer rate. Okay. Suppose if Ks is very high, so reaction rate is very fast, and we can do that by having appropriate temperature. Suppose a reaction happens very fast if we increase the temperature of the substrate, then by increasing the temperature we can increase the reaction rate coefficient such that if Ks is very high compared to Hg or the mass transfer, then my concentration will drop to 0 at the surface, okay, because reaction rate is very fast here. So, whatever is coming to the surface is reacting to give you thin film very fast. Okay. Now, if that is happening, then my thin film deposition rate will depend on mass transfer. Okay. Then this reaction holds. If Cs is 0, then it will depend on my mass transfer. If the reaction rate is very high, then my deposition rate will depend on mass transfer rate. On the other side, if my mass transfer is very high and reaction rate is very slow, then these two concentrations will become equal, okay, because my mass transfer is very fast and I am not able to use the concentration at the surface to convert into thin film at a higher rate. So, these two concentrations over time will become equal. If that happens, my thin film growth rate or the flux which is being converted into thin film will depend on reaction rate. Okay. So, in this case deposition is mass transport limited and deposition is reaction rate limited. Okay. So, there are two processes, mass transfer and reaction, and they are happening in series. So, one after another. So, the slowest of these rates will control the your deposition rate. Okay. Let us have a look at this in how we can use this information to adjust our deposition parameters. If you look at in this graph, the substrate temperature and for deposition of silicon from silane gas using different gases is shown. Okay. Now, if you see in this region, so this is a demarcation line of two different regimes. In this regime it is surface reaction control, okay, means mass transfer rate is very high. So, this is high mass transfer rate. Okay. If mass transfer rate is high, then it is controlled by surface reaction rate, and on the other side it is diffusion control, which means reaction rate is very high. Okay. So, these are two different regimes, and we can find a demarcation between them following the thermodynamics and kinetics of your reactor or by some experimentations. Okay. Now, what is important? That we want to have uniform deposition. Okay. For uniform deposition, my mass transfer should be very high, so that we can control the deposition rate by the, and my mass transfer should be high and reaction rate should be slow. Okay. So, that my concentration is distributed very evenly across the large area or all the wafers. Okay. So, that is one thing. However, if you see that if you are not able to control the temperature very effectively, if your temperature is varying at different places, then this reaction rate is dependent on temperature as minus Es over Kt. Okay. So, the reaction rate is an Arrhenius type expression. So, it depends on temperature exponentially. So, if there is small non-uniformity in temperature, it will affect your reaction rate to a large extent. If, since your deposition rate is controlled by reaction rate, then you will have difference in reaction rate or the deposition rate at different points, because your temperature is not uniform. On the other side, when you have high reaction rate, okay, so temperature is high enough that you do not worry about the reaction rate at all. So, whatever is transferred is being converted into your thin film. So, you are now dependent on mass transfer. Okay. Mass transfer does not depend on temperature to that extent, not exponentially. It is has a weak dependence of T to power D. The diffusivity or mass transfer had a temperature dependence of about 1.5 to 1.8 in that regime. So, once you have that diffusivity, not the exponential dependence, then you can work with small non-uniformities in temperature, but then your diffusivity should be very high. Okay. So, now depending on what you want, you can control your reaction such that it either is in diffusion control or mass transfer control or surface reaction control. Okay. If you can control the temperature very uniformly across all the substrate, it is always good to be in surface reaction control. Okay. But if you cannot do this, then you have to make sure that your diffusivity is very high and you work in diffusion control. Okay. So, with this we will stop here in this lecture, and we will continue our discussion using some of example. We will go into thermodynamics of the reaction in the next lecture. Thank you.